Great. Where were we last time? Yes, we saw the entropy of a random variable. It was defined to be so a random variable has a probability distribution. That's a lot of numbers. It's a bunch of numbers that sum to 1. You plug in all those numbers into the definition, and it spits out one more number called the entropy of the random variable. And how do you obtain it? You sum over all possible x's, p of x log of 1 over p of x. This was our definition of entropy, Shannon entropy. We obtained it as a minimization problem where we were interested in minimizing the expected length of a prefix code to communicate the outcome of that random variable. That was the context in which we were. Now, maybe I should just mention it, but we are able to exhibit the prefix code for a random variable x with expected length equal to the entropy if the probabilities are powers of 2, inverse powers of 2, like we had in the example. One of the questions in the problem sheet is I ask you, in general, those probabilities, those numbers will not be powers of 2. I ask you to exhibit a prefix code in which the expected length is going to be smaller or equal than the entropy plus 1 bit. So you can always find somewhat easily a code which has one more bit of expected length, even if those are not powers of 2. Great. Yeah, at this stage, I'd like to take. Was there any questions about what we've done last time? No. Okay, let's go with some properties of entropy. Yeah, first one is that it's greater than 0. How can we see that? Well, probabilities are greater than 0. And this quantity here, for all non-zero p of x, we will add p of x times log of 1 over p of x. 1 over p of x is going to be also greater than 0. Because p of x is going to be smaller than 0, so 1 over p of x will be greater than 1, or equal to 1, and so the log will be greater than 0. So each term we're adding we're adding up numbers larger than 0. In fact, we multiply two numbers larger than 0 together, but we add them up. Second, the entropy of the random variable equals 0 if and only if x is deterministic. That would mean that x is deterministic. There's only one outcome which has probability 1, and you can plug it in, and you see that for that outcome you have 1 times log of 1. That's 0. And it's in fact it's an if and only if. So you can derive the constraints on the possible p's such that it's equal to 0, and you'll find that there's only one solution. And a third property, if the size of the non-zero values, the size of the possible values that x can take. By possible values, I mean that values for which they don't have a probability 0. Okay, so cal x is the set of values that the random variable x can take. By the use of the word can take, there's an underlying assumption that the distribution is not 0. The probability, sorry, is not 0. So if this is kept fixed, then h of x is optimized, actually, by which I mean maximized, by the equiprobable distribution. In which case, h of x would be equal to log of the cardinality of cal x. So what does point 3 mean? Okay, if we forget just this first part, I try to maximize the entropy. And if I maximize the entropy, well, one obvious solution is to just add up some possible events and make my distribution, larger and larger and larger again. So if I constrain the fact that, oh no, there's only, for example, 17 non-zero outcomes, 17 possible outcomes, then the entropy is maximized by the distribution which is equiprobable. So all of the probabilities would be 1 over the cardinality of that set. Okay, we can verify that quite quickly, that if we in fact plug all the probabilities being 1 over the cardinality of cal x, what would I get? Just do it quickly. We have sum over all x and cal x. If I have the equiprobable distribution, then the probabilities is 1 over the size of cal x log of cal x. There you go. But this sum is now an empty sum because I'm summing constant things. So that would simply give cal x, which would cancel out this log, this 1 over cal x. It will give log of cardinality of cal x. Now the other way around is a bit harder. I mean, to show that it's maximized by the equiprobable distribution, but you can play with it and find it.
Excuse me, are you recording? Because as you are not here.
Yeah, I am. Thanks for asking. Yeah, and so far I've been quite lucky. I've pressed the record button at each beginning, of course, but thanks for reminding me. It'd be fun not to miss them. Great. And then point 4, I guess it's going to be the other side of point 3. If we fix that we only have equiprobable distributions, so 4 equiprobable distributions, the larger cal x size of cal x, the larger h of x. Right? So if I will have more entropy if I can have 200 possible outcomes equally likely than if I have 100 possible outcomes equally likely. Again, simply because this quantity increases. I guess that the reason why I wrote down point 3 and point 4 is more or less to get the general philosophy behind the entropy. So let me just write down that points 3 and 4 can be generalized I also say and informalized, if that's a word. Made informal rather than formal by the fact that the more uncertain a random variable, is, the larger is its entropy. Okay, in the case of point 3, the notion of uncertain was by the fact that the distribution was flat over all its possible elements. It was equiprobable, maximally uncertain. And the point 4 was to say that, oh no, I was not guessing between 100 possible outcomes, I was guessing between 200 possible outcomes. The more outcomes I have, the more uncertain I am. And that's like a generic feature of entropy. It measures, if you want, how uncertain a random variable is. And we can jump back to our operational meaning of entropy. If a random variable is highly, highly, highly uncertain, I can expect that the average code word length to communicate its outcome is going to be quite long. If a random variable is barely random, it's like, you know, we're very confident it's going to be that outcome, then I can have very short code word length for that outcome, and I can have expected code word length small, so small entropy. That's a generic idea behind Shannon entropy. Now, yes, things get more interesting once we can consider more than one random variable. So, definition, unless there's any questions so far. The joint entropy of a pair of random variables x and y is defined as, we just write it, h of x comma y, and that definition is not so hard because I can just really understand a pair of random variables as just one large random variables. You know, I think I mentioned it last time, but we can think of them as having a big arrays of number. This whole array of numbers sums to 1. And why it's an array? Because it, you know, it might encode on the x direction. The random variable big X has value little x, and in the y direction, the random variable big Y has value little y. I actually invoked the x and the y direction, but it happened that it also fit with my x variable and y variable. That was not really on purpose. Okay, so I just think of it as a huge, you know, random variable, and it's going to be the same notion here, but simply extended. So you sum over all x in x, all y in y. You can think of that as a two-dimensional sum. Or let me be more explicit. Sum here, sum y in y. And then I have p of xy log of 1 over p of x y. That is extremely analogous, as I said. Okay. If the random variable x takes value x hat so I'm really fixing one value for my random variable, and that value is little x hat. This defines, as we have seen, hang on. It's a small p. P of y given x of y given x hat or you can even think of it as might even stress my point more. P of y given capital X equals little x hat of y. It doesn't really matter in this case because I really fix x hat. So x hat is fixed, and for x hat I have a distribution for y, which is the distribution at the random variable of the random variable y given that x has taken value x hat. And it's a variable in the possible outcomes of y. I guess these are two, equivalent ways of writing it. Correct, okay. This defines this. And given each individual outcome, x hat in cal x of the random variable x, there is residual entropy. In the distribution P of y given x, y given x hat. Okay, so we've seen that we have conditional probability distributions. Now I'm writing a conditional probability distribution given a specific x hat. And that, by the very fact that it is a probability distribution, I could plug in that formula. And I have qualified that sort of a residual entropy. Like I have a pair of random variable x and y. X has been instantiated. I know, x has value x hat. But I still have a remaining, what would it be? A remaining line on my imaginary array of labeling all the probabilities of x and y. And that line would once renormalized, would be a probability distribution of this kind. And it has residual entropy. The conditional entropy, this is where I'm going. I want to define, we have an entropy for a pair. We have an entropy for a single random variable. I want to define a conditional entropy. Conditional entropy. H of y given x is the expectation over x of that residual entropy. In other words, or mathematically speaking, h of y given x is, oops,
We're going to sum over x, or what?
I made a mistake in my, oh no, this is fine. Okay, it's just, in my notes I had written an extra thing, which is going to be helpful to understand the mathematical formulation here. Sorry, there is residual entropy,
Yeah, the
and
notation.
here I denoted as h of, what is it? So it's entropy with respect to y, the random variable is y, but knowing that the random variable x has had value x hat. So if you want to insert that here. And now the conditional entropy, I'm not looking for the conditional entropy of y given that x has had a specific outcome. I want to define this, as a property of two random variables. So the idea is to average over those residual entropies. But by average, I average over the possible values that x can take. So I'm averaging over x of p of x, that's the expectation value of, and then I said of the residual entropy. So let me just write it. H of y given the random variable x equals little x. I could do one more line, if you want. Sum x in cal x, p of x. Sum, yeah, because now here in the definition of the residual entropy, there's a sum over y. Because that accounts for all the possible y outcomes. Y in cal y. And then we have p of y given x So I wrote the residual entropy.
So basically the inner sum in your array picture, the inner sum is like summing down the columns, let's say, and then the outer sum is summing over what's left, meaning the row.
Mm-hmm. At the end of the day, you do have a double sum. And I could have been more obscure by factoring out this, putting that in here, using the product rule, because then I would have p of x, p of y given x, that would just be p of xy, and then having that term. But then you don't really understand where this comes from. You will actually have to play with these sums in problem sheet number 1, where I ask to prove the chain rule. So one intuition that I can quickly mention about conditional entropy is that h of y given x is equal to 0 if and only if the value of y is completely determined by the value of x. So if the value of x determines what's the value of y, okay, it just so happens that x is a random variable and y is double that random variable. You found x, you go like, oh, I know what's y, you can multiply it by 2. So once you found x, the residual entropy will always be 0. There will be no surprise in guessing what's y. There's not going to be no undetermination. And vice versa. So if actually this thing is identically equal to 0, for a sum of p of x, it means that these guys need to be identically equal to 0. So every time you read out x, there is no entropy left to find out y. I'll leave the h of x on the board. Theorem, the chain rule. So the entropy of the pair xy equals to the entropy of x plus the conditional entropy h of y given x. If you want, if I have a pair of random variables and I want to appreciate the uncertainty of that pair of random variable, it's the uncertainty in one of them plus what's left as uncertainty. The uncertainty in y given that I already know x. And the proof is in the problem sheet. It's sort of a good context to manipulate those sums. And yeah, the tricky one is the conditional entropy. So you're going to make sure you understand what, maybe this formula now helps you a bit more to get to the desired result. Is there any question? Good. once we have entropy and conditional entropy, we can define the mutual information. Mutual information between x and y is, we denote it I of x semicolon y, and it's h of x minus h of x given y.
Sorry, do you mean something different, writing just the comma or the point and the comma?
I do. Well, for one thing, okay, I is going to be a quantity which has a point and a comma all the time. H, you will never see such symbol in H. So when you have H, there's two things that could happen. Either there's a comma, which means it's the joint entropy, it's the entropy of the pair of random variable, or there's this bar, which is the entropy of y given x. This bar really resembles the same as the bar we have in probability distributions, right? It's probability of y given x. And by the way, yeah, p of y given x also appears in here. Now for the mutual information, I'll justify why I write a semicolon and what does that mean. So yeah, it's the mutual information between two things, x and y. And yeah, it's equal to that by definition. So in short, you can right away appreciate that if y tells you a lot about x, okay, let's go back into the regime in which y fully specifies x. We've seen that this term will vanish, okay, because if you know y, there's no uncertainty left into guessing what's x. Then this thing is going to be large. It's going to be as large as the entropy of x. Whereas if y doesn't tell you anything about x, okay, y is, I don't know, the weather in 3 days from now, and x is going to be the price of ice cream in Kentucky, then they're independent, so that you expect that the entropy of y given x is the same as the entropy of x, because y is useless to help you predict what x is. And so you have h of x minus h of x, you will get 0. There will be no mutual information between x and y. I write that down. Yeah, it is the reduction in the uncertainty of x due to the knowledge of y. So that was the mutual information, and I'll go a bit more quickly. It's quite straightforward from there, but there's the conditional mutual information. Which is exactly that, but for example, you also have as background knowledge variable z. Why not? And we denote it like this. It's going to be I of x semicolon y. So it's the mutual information between x and y given z. And the given z is just, you stick it here, stick it here, stick it here. You just keep having z as background knowledge. So that's h of x given z minus h of x given yz. Okay, one of the good features about the chain rule is that it permits to have a symmetric notion of mutual information. Right now I've written I of x semicolon y, and so it's really a function of two entries, and it's sorts of, you know, in appearance it matters who's first and who's second. It's h of x, so h of the first entry minus h of x given the second entry. And thanks to the chain rule, this is symmetric. It's the same as I of y semicolon x. We will see why. So the chain rule entails that mutual information is symmetric. Why? So x of I of xy is equal to, now I'm using the definition, h of x minus h of x given y by the chain rule here. Oh, it's a bit confusing. I have it on the other side, but we'll be able to get there. I can simply write that h of x given y, which is what I will want, is going to be equal to h of the pair minus h of y. Okay, so if you're with me for a second, I'll quickly explain. I used that formula, but I inverted x and y. So it's h of y plus h of x. H of y plus h of x given y. It's the entropy of the pair. And then I isolated h of x given y by subtracting h of y on both sides. And from there you can, I'll just rewrite that here. H of x minus, here I've got h of y, xy, xy minus h of y. So that's the first application of the chain rule. And then minus h of y, that's plus h of y. I'm just going to rewrite it here. And I have minus, I'll keep this one here, h of xy. Oh, there you go, minus again, h of x. So in fact, I'll just keep this ugly way of writing it with a couple of minuses, but I just changed the role of this plus h of x is now a plus h of x here in the name of minus h of x. And then you can see by applying the chain rule again, what have we got? H of y. And here I have, then I can directly use that equation here, minus h of y given x, and that would be the mutual information between y and x.
There is a minus, there is a plus. Like third line, there is a minus. Like it's minus h of x, and above it's plus h of x.
Here?
It's just one, two.
I mean,
Put
you
out
have
the plus.
minus h of x, and above you have plus h of x.
Yeah, but I have
Okay,
minus
yes, okay,
parenthesis
yeah.
minus h of x. That's my plus h of
Yeah,
x.
because you just put okay.
Yeah.
But if you write it, if you write the intermediate steps, so you have like h of x plus h of I minus the joint entropy, right?
Yeah, correct.
Which
Yeah.
seems-
From here, yeah, I could have. It's good observation. You realize right away that it has some symmetry by, say, if I write it like this, h of x plus, so minus h of y is going to be plus h of y minus h of xy. Yeah.
Yeah, it seems very similar to the size of the union, for example.
Uh-huh.
It's like
Oh.
the size of the sum of the size of both sets minus the intersection.
Okay, I was about to take the break, but since you brought it up, and since Will is there, we're gonna have a diagram. Yeah, it's a good point. A good point. So once you have those notions and you realize that, oh, it looks like stuff that can be represented by diagrams, how am I going to use colors? Just start with black. Yeah, one way to represent the entropies and the mutual information is to represent, if you will, the uncertainty in my random variable x. So this whole thing would be h of x. And then the uncertainty in my random variable y, this whole thing would be h of y. What's in here is h of y given x the union of the two is h of xy. This one here would be h of x given y. And in the middle, we could represent this by the mutual information between x and y. So why am I writing all of this? It fulfills the algebra. That's just the basic idea. Why does it do that? Well, okay, let's check. If I claim that the whole is h of xy, well, I can express the whole as h of y in blue plus h of x given y in black. Well, in black except this part. Or I could have done the chain rule the other way around. I could have said, oh, it's h of x, the whole black region, plus h of y given x, the green region here. Or we can see, oh, what's the mutual information between x and y? Well, by definition, it's h of x, the whole region in black, minus h of x given y. Yeah, it works. That's what's left. It's the mutual information. So if one likes to think diagrammatically, this diagram represents faithfully the algebraic relations that entropy and mutual information satisfy. Okay, that was a lot of definitions. h of x, y, h of x given y, I of xy given z. I think that's it. One of my main reasons there exist courses on Shannon information theory, and not only you define those, but then you see what they mean when you have noisy channels. So a channel which, if you give it as an input some string x, with some probability, well, the output is not going to be the same. There's going to be a distribution as a function of x. And then you can quantify statements that would rely how much do you need to put redundancy in your encoding? Redundancy meaning that you would want to make your code words a bit longer than the shortest minimal one, so that you can decode them without error. You know, like if I have a noisy channel and I want to send you a very, very, very important bit, I'm not just going to send it only once. I might, replicate it 7 times and say, well, to decode it, you take the majority of those 7 bits. If you read like 6 ones and 1 0, then you will correct that to, oh, what I meant was a 1, and maybe by error, one of the bit has been flipped. So, all these concepts appear when one develops the full theory of Shannon information theory, which, as I say, may have a link with noisy channels. Now, this is not exactly my motivation, though. I introduce these notions because they will crop up again in the algorithmic setting. We will see something which is the mutual information between x and y. But in the algorithmic setting, x and y will not be random variables. They will be fixed bit strings. And there will be a notion of the chain rule. So, as I say, I said that on the first course, but the analogous of Shannon entropy will be Kolmogorov complexity or algorithmic complexity. And this relation will crop up again. So this is probably my motivation to introduce those notions to, so that you're aware that they have a meaning in the probabilistic setting, and we will revisit it in the context of algorithmic information theory. However, I'd rather spend, more time and details once we see them in the algorithmic setting than spending time and details once we see them probabilistically. So that's why I don't do like plenty of examples with those concepts. We will get to one though at the end of the day. Lost my sheet. Here it is. Are there any questions so far? Okay. I think I'll start. information inequality. It can be shown that the mutual information between x and y is larger or equal than 0 and equal to 0 if and only if x and y are independent. I gave a cartoon just before the break. I said if y is the weather in 3 days and x is the sales of ice cream in Kentucky, then we expect that mutual information will be equal to 0. Well, I displayed, that cartoon was basically displaying two x and y that are independent, qua probability distribution, so their probability distribution factorized. And it entails that the mutual information between x and y is equal to 0. Now this statement says that if it's equal to 0, then they are independent. It's quite a remarkable property because once we write down the independence for the distribution, it's a bunch of equalities. You know, that x and y are independent, it means that p of xy factorizes as p of x, p of y. But you know, this equation holds for all x in cal x and for all y in cal y. You know, this as a distribution is equal to this. But here we only have a number to compute out of those distribution. And if that number is equal to 0, then they're independent. Also, what it means is that thus, or maybe I should say thus, h of x is larger or equal than h of x given y. If this quantity is larger or equal than 0, well, this is larger or equal than 0. So this one is larger than that one. To put words on that, I could say learning y on average doesn't harm to predict x. Okay, I don't show the information inequality. You can find it in the cover in Thomas if you want. Now that you have the name, you could also Google it if you're curious. But I want to move forward. It's still a useful idea to have in the back of our mind. Another idea which will actually merit a definition the random variables x, y, and z form a Markov chain denoted x arrow y arrow z if the joint distribution factorizes as so we've got P of x, y, z, that's the joint distribution. We have three random variables who are claimed to form a Markov chain. The notation is really helpful to understand what's going on. And it's P of x, so you can think of x as being a first random process. And then y will depend on x. So P of y given x. In fact, this equation always holds for P of xy. But then here, what this diagram means is that z, if it depends on x, it's only via y. So P of z given y. And by the way, yeah, so this means it seems like there's a lot of assumptions into this factorization. In fact, there's not many assumptions. There's only one. This means that P of z given xy is equal to P of z given y. Or, in words, or that z is conditionally independent of x given y. Okay, so a distribution like that always admits a factorization of the form. You can start with P of x, and then you have P of y given x. If I would stop here, by the way, and you multiply those distributions, you get P of xy. Now, if I want to get a third one in the dance, namely the variable z, I would need to add P of z given x and y. But here I just have P of z given y, and this is due to, so another way of putting it is that P of z given xy is equal to P of z given only y. Or in words, z is conditionally independent of x given y. If you want to predict what's going to happen to z, knowing y, well, you don't care what was x. This is a central idea in causal diagrams. For those who know maybe the literature of Judea Pearl, I know some of you are in machine learning, you will use like those arguments. So if you want to predict, for example, that was a classic example in his book, if you want to predict if one has cancer, z is cancer, and x is smoking, well, one of the ideas to establish causality between smoking and cancer is to have a mediating variable. And they found one. Y could have been like the tars in your lungs. So if you want to predict if one has cancer, to learn if this person is smoking or not is irrelevant so long as you know if he has tars in his lung. So then from there you can infer like a causal structure, which smoking will affect the tars in your lung, and the tars in your lung will affect your likelihood of having cancer. That's just an idea, just a comment basically to justify the use of that notation, which is somewhat useful. Great. theorem, the data processing inequality. If x arrow y arrow z, then the mutual information between x and z, sorry, I'm going to be consistent with my notes, x and y is larger or equal to the mutual information between x and z. If you are to, there's a relation between the variable x and the variable y, possibly. If you are processing y to get z instead, you will only shrink your amount of mutual information that you have with x.
Sorry,
Yes.
but in this context, what's the meaning of the symmetry of the mutual information? So, for example, if you have a time arrow, I mean, you should.
There is no. In fact, the notation suggests more than just that equation here. The notation suggests that x is the father of the variable y, which would be a child. But when you look at that, nothing really says so. Oh, sorry. Being factorized this way, yes. But the only thing that you have is a conditional independence between, I'm going to get it right, between z and x given y. There are other causal structures which would also lead to this same conditional independence. For example, I could just flip the arrows. If I flip the arrows, I would get that x is conditionally independent of z given y.
Yes, but then the conditional probabilities are not necessarily equal. You are considering like a reverse chain, so the rates can be different. It depends on the nature of the conditional probabilities.
Oh, yeah, I might have said something wrong.
It should be like in little bounds.
Let me think about it. If we have p of x, y, z, but I want to represent z, y, x, or to be even more tendentious, this. Like the natural thing to write would be you have first p of z, and then p of x of y given z, and then you have p of x given y. Right? This would be sort of the idea. You have first a random process z, which would be your father variable, and then depending on z, perhaps probabilistically, you can define y, and then depending on y, perhaps probabilistically, you can define x. But then the only assumption I've been using here is that p of x given y z is y and z is equal to p of x given y or in terms of statistical independence, I said that x is statistically independent from the variable z given the variable y, which I think is the same as what I wrote down here. Yeah, x is independent of z given y. I didn't want to go too much into the details of that. Let's take this as it is, and you can understand it as I explained it. But really, like the real assumption for the probability distributions is that one. Okay. But yeah, please, we could check that further if you want, if you're unsatisfied. Cool. Okay, so if we have a Markov chain like that, then the mutual information between x and y is larger or equal than the mutual information between x and z. Let's prove it. It is not so hard, and it gets us to work a little bit with the definition we've seen. I think what touches on the issue is that for a given set of independence relations or conditional independence relations, more than one causal structure is possible. And when I write it down like this, I'm sort of giving you the idea that that is the causal structure. It's x who gives, affects y who affects z. But yeah, it's not necessarily unique. So in other words, if you really see a statistical independence between smoking, so predicting if one has cancer is irrelevant whether he smokes or not, given that you know if he has stars in his lungs or not. It might be that the causal structure is that having cancer causes stars, which causes you to smoke. I remember that's sort of a thing I read in Julia Pearl's book. But you sort of have to come with other arguments, like, come on, like just mere statistical independence could not, discard which causal structure is the right one. But come on is, it's an argument that still needs to be formalized. Great. Where was I? Okay, so the proof. Okay, it seems like I'm going out of nowhere, but let's do it. Let's assume it. You have to know it. Let's look at the mutual information x, y, given z. And we will write it from two different ways. So, this is k of x. No. I'm sorry. This is not what I want to write. I want to write a comma here. So I'm curious about the mutual information between x and the pair of variable yz. By definition, this is k of x minus
You mean h of x or k is Kolmogorov?
I'm so used to that. Yeah, we're gonna get there. H of x minus h of x given y and z. Okay. There's a trick here, and it's to rewrite h of x minus h of x given z plus h of x given z minus h of x given yz. I basically inserted 0 in the middle. I did minus something plus the same something. And this is equal to, so that is the mutual information between x and z. And that also has a flavor of mutual information, which unfortunately I had erased, but it's the conditional mutual information. Z is always given in this context. So the trick is to realize that, oh yeah, Z is always given. I'm going to put it right here, you know, given Z. And then you have h of x minus h of x given y. Well, that's the mutual information between x and y. I left it blank because another trick is to realize that I could also have done h of x minus h of x given y plus h of x given y minus h of x given yz. I rewrote a very similar equation, but instead of inserting nothing as this nothing, I inserted nothing as that nothing. Minus h of x given y plus h of x given y. And then it's extremely analogous to what I just wrote above. It's mutual information between x and y this time. That will be the first two terms. Plus the second two terms, I have a mutual information given y, because y is always given. But then I have entropy of x minus entropy of x given z. So that's mutual information between x and z. But now we're going to use the fact that it's a Markov chain. Since it's a Markov chain, it means that z is conditionally independent of x given y. So by the data processing inequality, that's what we want to show. By the information inequality, they're independent if only if their mutual information is equal to 0. But now it's not the mutual information, it's the conditional mutual information. That one is going to go to 0. Because x is indep of z given y. And since the other conditional mutual information, I of x, y given z, is larger or equal than 0, this is a quantity which is larger than 0, larger or equal. So this one here, I of xy, is larger than that one here, I of xz.
said x is independent of z given y, but it seems like we're going the wrong direction. Isn't x supposed to be the first one in the chain? Like on that board, it's the other way. We have z is conditionally independent of x given y.
Yeah, good. Nice. I can change them. Oops, now I have a black marker. It's a symmetric relation.
Yeah, because it's symmetric. The colon is symmetric.
Yeah. You can either work it out with the distributions to see that if x is independent of z given y, then x is independent of x given y. Or you can invoke this and the symmetry of information. But it's the same. Okay. We have a corollary. In particular, if z is equal to some function of y, some deterministic function of y, we have a Markov chain because g of y is conditionally independent of x given y, correct? And so I of xy is larger or equal to I of x g of y. I actually like to say that I of x g of y is smaller or equal than I of x y, which basically says that you can't hope to process your information to increase the mutual information with x. I said the word information. You can hope to process your variable y in a way that you will increase your mutual information with the variable x. Another way to think about it is if x and y are two independent dice, there's no function you can define on your second dice to hopefully start having correlation with the first dice. They will remain independent. Because if they're independent roll of dice, this quantity is 0, their independent variable, and you can only decrease it, but it has to stay positive. It will remain 0.
But intuitively, I think that equality holds when G is bijective, right?
Correct.
I don't see how to prove it. Anyway.
Next problem sheet. No, I guess we're going to be somewhere else. The next problem sheet. But if G is a bijective map, it sort of preserves the information into Y. You haven't discarded anything. You're fine. Things can get messy if G is sort of a many-to-one map. You might have lost some information. Exactly. And so I'm just going to briefly comment on what I said. It is impossible to increase the mutual information between two random variables by processing the outcomes in some deterministic manner. And also in some probabilistic manner. I'm just going to write more probabilistic. So the deterministic appeals to, this corollary where z is a function of y, but the probabilistic manner has the meaning of if you process it this way by some random process. So z could be thought of some random process which depends on y. Any questions?
Probabilistic in the sense that, the randomness that I use in the process is independent of y, right?
Yeah. Yeah. I don't know if that really boils down to some philosophy of probability, but I like to think of a probabilistic process as a deterministic function of y and some extra thing which we don't know, which might have its own distribution to add, randomness into the process. I will stop here. But just before we go, I'd like to advertise I put on the Dropbox of the group a paper, an old paper, Alan Turing, 1936. And it's quite rare that we can read a paper almost 100 years later and go like, wow, what a brilliant paper. But this one really qualifies. Especially if you're computer scientists, I assume all of you are. He's probably the seminal paper of all our field, and in which he established the basics of computation. Have a look at it. It's on the Dropbox. You could also Google it, Alan Turing 1936. It's called Uncomputable Numbers, an application to Entscheidungsproblem. We will do that next time. So we will switch topic to computability theory next time. But it's good to have a bit. It's going to be more fun if you have had a read of it. Now, I wouldn't recommend to read it all because there is a lot of technical parts about how Turing machine moved their head, and you don't really need to read that. You can if you want. But have a look at sections 1, 2, 9, and 10. It's basically the sections in which there are words. So there's no machine programming in the sections 1, 2, 9, and 10. And I guess it's gonna enhance next time's lecture if you have had a look at it. So, yeah, I guess that's it. Is there any question for today's course?